Okay, hello. So in this video, we're going to be taking a look at right triangles and some properties in particular regarding trigonometry. We're not going to be doing too much in terms of the similar right triangles. I'm going to talk very, very briefly about that. I'm just going to get to the extremely important concepts for Chapter 7, and that's namely the trigonometric ratios, which you'll see in a little bit. That's where the words come from. So just to highlight the language here, tri means three. So triangles have three sides. Trigonometry is basically geometry that involves three-sided figures. That's why we're looking at triangles. In particular, right angle triangles. So that's the more important aspect in terms of the concept we're going to be looking at. So the whole idea of some of the things you're going to be looking at is that when you resize a triangle, oftentimes the proportions remain the same. So what do we mean by that? Well, that means that there's a relationship between the ratio of the sides that are consistent. I'll show you which ones are consistent in the couple of minutes ahead. So the statements that I have listed here are basically telling me some key properties from your previous course in terms of what angles are the same and why are they the same. So you may remember patterns like F patterns for corresponding angles, and then Z patterns where you have alternating angles of the same. And obviously if you don't remember any of those, it's not a big deal, but some of these things, so this is a given one. So in different triangles, you have different triangles here. There's triangle ABC and triangle BDE. So this is just kind of relating the different angles that are in them and why they are the same. And if they are the same, then we call these triangles similar. All right. So when you have similar triangles, there's relationships that exist that you can take a look at. So we're given some information about the lengths of certain sides in triangle BAC, this one here, and triangle BDE. So when you create ratios in these triangles, and these ones are very specific, so we're relating AC, this one here, and BA. So in a right angle triangle here, this BA is actually the special side. We'll get to that name in a minute. And then if we compare the same kind of ratio, so in other words, the special side that's opposite 90 in triangle BDE, so this one here, BD, that one there, which is on the bottom, and we compare it to DE. Now, how you compare them is important as well. So you notice the numerator has the vertical line measurements, and then the denominator is the diagonal lines or the special lines that are opposite the 90 degrees, which we're going to remind you what the name of is in a moment. Okay, and once you compare these ratios, you notice they're exactly the same. So the proportion, that's what I was getting back to in terms of talking about proportions. So they are the same, and what we focus on though is this angle right here. So this angle is very important. So this angle and that side have a relationship. They are opposite one another. So think of sitting at a dinner table, you're opposite someone on the other side. So think of it that way. But this angle is also opposite the other side, DE. All right. So in their respective triangles, they are, the AC and DE are opposite angle B, and also the special name that I'm sure many of you knew about, BA and BD, they are hypotenuses because they are opposite the 90 degrees in the right angle triangle. So because these two things, the BA and the BD, they were used in the ratio, and the AC and the DE, and they were used in the ratio, we create a named ratio. So now we have generic names. So the side opposite angle B, oops, I missed that. So the side opposite angle B divided by the hypotenuse gives us a ratio. And it doesn't matter which triangle we're looking at, whether it's the smaller triangle or whether it's the larger triangle, we get the same ratio. So because of that special property, we kind of shortcut the naming of it. We refer to this ratio as the opposite side divided by the hypotenuse side. So it's the length of these sides. We call it a sine ratio, S-I-N-E, okay? And then similarly, in a very similar fashion actually, we're going to take a look at the relationships between other sides in the triangle. And this time though, we're relating again, with angle B, we're taking a look at something called an adjacent side and the hypotenuse. So just to go back to this diagram here, so again, this is kind of like your reference angle. So AC is opposite angle 52, and so is DE. But now we're talking about these adjacent sides. So this side right here, BC, is adjacent, which means kind of connected to or joined to, beside, but it's also adjacent to BE. Okay, so all these sides are given a special name, and that allows us to create these special ratios. So the first ratio was the opposite side divided by the hypotenuse, this one here. And then the next ratio we're going to take a look at is the adjacent over the hypotenuse. And in a very similar way, it doesn't matter if it's the bigger triangle or the small triangle, the ratios are the same. We give that a fancy name called cosine. Okay, so we've seen two different ratios, one called sine that involves the opposite side and the hypotenuse relative to a reference angle, and the cosine ratio, which is the adjacent side and the hypotenuse relative to a particular angle. There's one more ratio we're going to take a look at, and again, this is just a reminder what the side lengths are, so don't worry too much about that. But the other ratio that we're going to take a look at takes into account the opposite of angle B and the adjacent. So that's the pairing we haven't taken a look at. So the opposite and the adjacent. So comparing these two. So we're leaving out the hypotenuse in this ratio. This ratio has a different name, of course. We call this the tangent ratios. Okay. So, and again, the actual ratios themselves are equivalent. Doesn't matter if we're looking at the large triangle or the big triangle, but we have to have a reference angle. Always have to have a reference angle. So that gives you a brief overview in terms of what we call the primary trigonometric ratios. So the names are sine, cosine, and tangent. Okay, so again, now the key names that we also looked at are opposite side and adjacent. Hypotenuse you're already familiar with. The words opposite and adjacent, though, they're important because you have to have that reference angle, all right? So just to make sure we talk about the side lengths again and give you a little abbreviation too. So the ratio named sine refers to taking the opposite side of an angle in a right angle triangle, but not the right angle, that's important, and dividing it by the hypotenuse. And that ratio is referred to as a sine ratio. And whatever number that is, it is. And it'll be the same ratio regardless of making the triangle a little bit larger or smaller, scaling it down. Cosine ratio takes the adjacent side, divides it by the hypotenuse, and the tangent takes the opposite and divides by the adjacent. Now this allows us to create something called an acronym, which can be used to remember these ratios. So sine is the opposite side divided by the hypotenuse. Cosine is the adjacent side divided by the hypotenuse. And tangent ratio is the opposite side divided by the adjacent. All right, so we'll take a look at that in a follow-up example. And if you put that acronym or those letters together, you get something we in math sometimes pronounce and often pronounce SOHCAHTOA. Okay, SOHCAHTOA. All right, so there's the SO, CA, and then TOA. So the last two are really for the tangent, last two syllables anyways. So the way we set up formulas in this is what I've got here. So you need the abbreviation name for the type of ratio you're looking at. You have to have that reference angle, and then you write down a ratio. So for the examples you've seen earlier, in triangle ABC or BAC, whatever you want to refer to it, and using again those numbers that are given to us, the sine of angle B. So again, sine is opposite divided by the hypotenuse. So the length of the opposite side divided by the hypotenuse, there's your ratio. Cosine of angle B is the adjacent side divided by the hypotenuse. There's the adjacent length and the hypotenuse length. And the tangent of angle B is the opposite length divided by the adjacent length. Okay, so that just gives you a little insight into how the ratios work. So we're going to take a look at a concrete example now, show you how this works. So if you're given this triangle, now one thing that's really important to identify is the right angle. So the right angle 90 degrees is right there at angle B. Okay, so that's important to note because when you're coming up with these ratios, so you want to write the three primary trig ratios in terms of angle A. So there's our reference angle. So the words that we were looking at, the opposite, the adjacent, those are going to be important for angle A because it's going to be different for angle C. The hypotenuse is always across from the 90. So if we're trying to find the sine ratio for angle A, sine of A means, now there's the acronym, sine. I want the opposite side, 3, and then the hypotenuse, which is opposite the 90, is the 5. So I set up the ratio of those two numbers. So those two numbers would produce 3 over 5. Okay, so again, sine is going to be opposite over hypotenuse. Cosine ratio is the adjacent over the hypotenuse. Now again, this is for angle A. So this would be the adjacent to angle A. And then the hypotenuse stays the same at 5. So adjacent and hypotenuse produces this ratio, 4 divided by 5. So again, 4 is the length and 5 is the length. And we have adjacent over hypotenuse. And last thing is tangent, which is opposite, again, opposite the reference angle. So opposite A is the 3, and then adjacent is the 4. Okay, so opposite and adjacent. So 3 over 4 would be our ratio. All right, so that's how we find our primary trig ratios in terms of angle A. Now, if that angle happened to have a measurement like 23 degrees, then we would write sine 23 degrees equals cosine 23 degrees, and so on. And also the other important thing is if we were referring to angle C, then opposite C would be 4. Okay, so then these ratios would be different. So that's important to note. Okay. Your calculator, you might have noticed a long time ago, had some funny buttons on it. So I'm just going to demonstrate how you calculate these using your calculator. So the sine ratio of 63 degrees. So what does that mean? That means if you have an angle, and we'll just use angle A up at the top here. So if this angle was 63 degrees, what would be the ratio of the opposite divided by the hypotenuse? And that's what this number represents. And your calculator, now I got a very fancy one, but to locate these things in terms of the names, so there's the abbreviation SIN. Okay, so SIN is what you're looking for in terms of utilizing the sine ratio. So on your calculator, because it helps to put it on, sine of 63, and you'll get your answer. Now, I have a very sophisticated calculator showing you here. A lot of calculators that are not this sophisticated, what you're looking for in the display, somewhere in the display area, is either the word DEG, DEG for degrees, or just the letter D. You'll have to check your manual to get that set up. In my calculator, I have the mode here set to something that's not degree. So that's why the number didn't appear correctly. Okay, and that's why it's important to make sure yours is set up. So watch, I will change this now to degrees. Notice this number did not match what I had here on the screen, so I'm going to try that again. Sine of 63, and that's why it's super important you have this degree mode. You can reset your calculator, it'll automatically go to degree mode. Mine doesn't though, because it's a little bit more sophisticated. And there you go. All right, and to 4 decimal places was the requirement, so 8910, and that's what appears on the screen. All right, so it's as simple as that. Some calculators will require you to enter the degrees first and then press the button that you need. So on some calculators, you may need to enter 42, like in this case, and then press the tan button. That doesn't work on mine that way though. So, okay, so on my calculator doesn't work that way. You're gonna have to check to see how it works on your own calculator. So it'd be very important to look into that. So on mine, I could enter the tan button and then 42. And since I've already changed it to degree mode, it should give me the correct answer, and it does. Okay, and then similarly, cosine of 75, don't even need the final bracket, and it'll give me the correct answer. Okay, so please make sure you experiment with your calculator to get the proper results. Okay, so what do you do with these sorts of things? Well, they come in handy quite a bit, so I'm going to show you another calculator little trick here. since you can find the ratio, okay, so in these examples, you were given the angle, and we found the ratio as a decimal. What you're given in this next sample question is you have the ratio, but you don't have the angle. There is a way to do that using your calculator. And again, I'll demonstrate that using this one here. So it's referred to as an inverse operation. So you've heard of inverse operations, like adding is the inverse of subtracting, dividing is the inverse of multiplication, and so on. So the language shouldn't be unusual. So this statement is saying that the sine ratio of angle A is 0.9980. This statement is basically saying, so angle A must be the sine inverse of that same number. So in my calculator, if you look right above the SIN, there's an SIN with a -1 there. That's sine inverse. So I'd have to enter that decimal, 0.9980, and I will get my angle measurement. And of course, it'll have some decimals in there. That's okay. But I rounded it to 86 degrees because it said round to the nearest degree. Okay, and then you just repeat the same process. Again, some of your calculators will work a little bit differently. You might want to check the manual on how that works. So just to do this quickly, so cos inverse of 0.7071, 45 degrees. And then the tan inverse of decimal 4663, about 25 degrees. Okay, so please do yourself a favor and take a look at how your calculator works. Because notice this question is going to require you to do some calculating with your calculator. Okay, solve for x to one decimal place. So what is x? Well, x happens to be a side length. Now, we cannot use Pythagorean theorem. We have one side length here, but we do not have this side length. But we do have the angle, and this is where these ratios become very helpful. So we have an angle of 35. I'm trying to find this x, which is opposite the 35, and the 15 is adjacent to the 35. So opposite adjacent. If that reminds you of anything, hopefully it does. It's a cosine ratio. So the cosine of 35 is the opposite side, the adjacent. So again, the cosine ratio is the adjacent over the hypotenuse. Now, you might be saying, well, how helpful is this? I have to find x, and AC doesn't even involve x. Well, you're going to need a little bit of work, and it will work, but you need the Pythagorean theorem, and it gets a little bit more complicated. Okay, so you're trying to find a ratio that's going to work for you nicely. So again, as I said, you have the opposite to 35 and the adjacent, and that is your tangent ratio. Opposite includes the x. We have the 15, we have the 35. So that allows us to solve this equation easily because I can use my calculator to find the tan of 35. Using inverse operations, multiply both sides by 15, get an x value that I need. Okay, so this could work, but you need Pythagorean theorem, and unfortunately we don't have this side. If we did have that side, then you could use it, but then you'd also could use a Pythagorean theorem. So this is the one thing about these ratios. You do have to realize when is it best to use one ratio, one technique over another. Here we're asked to find angle A. Now, just like we found angles up here, we were able to find angle measurements. We're going to need ratios. Doesn't seem to matter which ratio we use to, we can always find an angle. But we only have two side lengths. So relative to angle A, I've got the adjacent and the hypotenuse. So adjacent and hypotenuse. What letter went in front of there for that SOHCAHTOA? Well, it was cosine. My apologies. I think I named one wrong. So let's try that again. The 5 is opposite and the tan is the hypotenuse. That's why you're using the sine ratio. My apologies, made a little boo-boo there. So these opposite and hypotenuse are given to us. Could find the adjacent using Pythagorean theorem if you wanted to, but this will work out just as well. So we need to find angle A. This gives us an equation that we can find it. How? Well, there's our calculator again. So we need to do an inverse function, much like we did previously up here. And that's the sine inverse of 5 divided by 10, and that gives us 30 degrees. Okay? So you're going to need your calculator a fair amount to get through this and get through it efficiently. So again, finding angles, eventually you're going to need the sine inverse. All right? Finding side lengths, you can try to use Pythagorean theorem if possible, or use one of the ratios that fits. And sometimes it's a trial and error to see which one fits, but again, you may want to name things. So in this one here, we have the opposite. Oops. And we also have the adjacent. This will be the hypotenuse. So once you label that and you know your acronym, your SOHCAHTOA, it'll narrow it down in terms of what ratio you should be using. Same idea here. I've got opposite and hypotenuse, so that would lead me to the sine ratio, or SO, opposite and hypotenuse. So there's the opposite side, the hypotenuse side. Go ahead and solve the equation using the technique shown.